The next step here was to perform the random walk process. As you know, in the Monte Carlo method, the first step is to discretize the governing equation. Here you have to discretize the boundary conditions as well. The second step of the Monte Carlo method is to perform the random walk process. Okay, then you can perform the random walk process using the fixed step method as before, but in some complex applications, such as the systems involving curved boundaries, you may choose another version of the random walk process, which is called the floating point random walk or the variable step random walk process. I will briefly introduce the floating random walk process here, and for more details about this type of random walk process, you can read Chapter 8 of the Numerical Heat Transfer Handbook, Chapter 8, which is devoted to the different Monte Carlo methods for the heat equation or heat transfer problems. In that reference, Chapter 8, these floating random walk process has been explained in more details. Okay, as you see, this is our geometry. This is the left wall. This one is the right wall. And we are going to compute the temperature of this one. This is the initial starting point of the random walk process. But this time, I don't have a grid. I don't have a grid network. I don't have grid spacing or anything else. So I want to perform the random walk process using two-dimensional polar coordinates. In this part, I just explained the two-dimensional case. You can easily extend my explanations to three-dimensional cases using the spherical coordinates. So here is the initial point. I want to compute the temperature of that point. So I start my random walk process from that point. The coordinates are x sub I and y sub I. And in this case, I want to proceed the random walk process by generating a random walk process based on the polar coordinates. So at the first step, I have to compute the shortest distance between this point and boundaries. For instance, the shortest boundary or the nearest, the shortest distance or the nearest boundary is the left wall. So this is the variable Ri, which is the shortest distance between the new point or the random walk point and the nearest boundary. This should be computed using a computer algorithm to find the distance between the point and the nearest boundary. And this is called R sub I. Then draw a circle. The center is the point and the radius is computed. So then you can transfer from or move from the center of the circle to any of the points located on the surface of the circle based on the random number generation. So you have to generate a random number and then multiply it by 2 pi, twice pi, because the all random numbers are between 0 and 1, and the angles along a circle vary between 0 and 2 pi. So then multiply it by this factor, and phi is the random number which specifies the next location of the random walker at the next step. For instance, here is the origin of the angle phi, so approximately 20 degrees, I think. This is phi, which has been computed completely randomly. And then move the random walker from here to this point. This is the circle, and this is the random number. This is the next position of the random walker at the next step. Then repeat this process again. And you have to compute the shortest distance between this point and the boundaries, the nearest boundary, which in this case may be the right wall. So in here is the blue circle. this other r sub I, and then again generate a random number and define the third position of the random walker. For example, is here. Then again compute the distance between the point and the wall and go on. This is the process of the random walk process in two-dimensional case. Using the polar coordinate relations x sub I plus 1 or the x position of the random walker at the next step equals the previous position plus Ri, I've explained the definition of Ri, cosine phi I. Phi is a random number, but Ri should be computed based on the geometrical details. And similarly, the vertical, the position of the random walker at the next step, and so on. For the spherical coordinates, the main algorithm is similar, but these definitions should be modified for the spherical, based on the spherical coordinates. This is the second step of the random walk process, but this time using the floating random walk process. Other details are similar to the fixed step random walk. And the final step, or the third step of the the Monte Carlo method, is to compute the temperature of the point or the initial point based on the wall temperatures obtained at the end of n random walk process starting from that point. So the temperature of the initial point, which was x sub 0 and y sub 0, equals 1 over n. This is the summation from n equals 1 for the first random walk to the nth random walk process. T sub w is the temperature of the wall at the end of the random walk processes, and n shows the counter of the random walks. This is the average of temperatures of the walls at the end of random process. Encounter the source term in the equation. Here you have to add another term to this temperature and to compute the effect of source term Q in the equation during the random walk process. Again, plus 1 over n. The first summation is over the random walks, starts from 1, ends at n. And the other summation shows the process of traveling during each random walk process. L shows is a counter of the random swapped steps during each random walk process. L from 1 to m, n is the number of steps for the nth random walk process. Q is the source term of the equation. R sub n and L shows the shortest distance between the point and the boundary, as you know, raised to, and the denominator is S shows the dimension of the equation for two-dimensional and three-dimensional equation. This parameter equals 2 and 3 respectively, and K is the coefficient here. Is the coefficient of equation or the thermal conductivity in heat transfer. So this step is for both two-dimensional and three-dimensional cases. You have to just change this constant at the denominator 2 or 3 for two-dimensional or three-dimensional cases. But this step is just for two-dimensional. For three-dimensional cases, you have to change these relations based on the spherical coordinates. And also in three-dimensional cases, you have to generate two random numbers for two spatial angles, phi and theta. But in two-dimensional cases, you can determine the next position of the random walker by just generating one random number. And as I told you, this process is very helpful in handling the curved boundaries.